Great. So I'm going to be speaking about two statistical challenges in classification of variable sources. I'll start off with some background on automated variable star classifiers and on automated classification in general. Discuss an example of using a CART to classify OGLE sources. Those first two sections will provide some background, and then I'll discuss two challenges that are common with variable and transient source classification. And those are controlling computational costs in feature extraction and post-classification inference. So a little overview of terms that are used in the classification literature. There's training data. This would be light curves of known class. And there's unlabeled data. That's light curves of unknown class that we want to classify. And the steps in classification, there's first a feature extraction step where we derive quantities from light curves that we know are useful for separating classes. So these would be things like period, amplitude, or derivatives of light curves. And then we have these features for all of the training data. And what a statistical classifier does is it constructs a function using the training data, and I'll call that function C hat. So this is the classifier. And that classifier maps from feature space to classes, either a hard classification like this is a Lyrae, or to a probabilistic classification. And then in the third step, we apply this classifier to our unlabeled data to determine classes. So the training data could be something like an archival survey, SDSS stripe 82, and the unlabeled data might be LSST data. Steps 1 and 3, I think, are pretty clear. Step 2 is sort of where the magic happens. How do we construct this classifier C hat? So I'm going to discuss one method for doing that. And that method is called CART, Classification and Regression Trees. CART was developed in the 1980s. And what CART does is it partitions feature space in an attempt such that the elements of the partition contain objects only of a particular class. So I'm going to show how CART works in a simple example with two features, feature X on the X-axis and feature Y on the Y-axis, and three classes, blue triangles, black circles, and orange plus signs. So what CART does is it searches across feature X and feature Y and attempts to find some split that minimizes misclassification or optimizes some other criteria. So when CART looks at this simple example, it finds a split along feature Y at around 0.4, and all objects with Y is less than 0.4 it assigns to a blue class, and all objects with Y is greater than 0.4 it assigns to an orange class. So this is the initial partition that CART makes for this feature space. And that partition can be represented by a tree. So CART stands for Classification and Regression Trees. And this is the, as CART is making more partitions, it's going to grow a tree here. So the initial tree is very simple. Y is less than 0.39 blue class, Y is greater than 0.39 orange class. What CART does at subsequent steps is it tries to further subdivide the elements of this partition, and again, in an attempt to find elements that are contain objects of only one class or minimize misclassification rate. So the next cut that CART makes is on feature X within Y is greater than 0.4, and it assigns objects to that are less than X is about 0.4 to the black class, and X is greater than 0.4 to the orange class. And this cut itself can also be represented on this tree. So for objects that have Y greater than 0.39, so that's objects that are all up here. Then CART makes a cut on X. Objects that have X less than 0.36 are assigned black class, and X greater than 0.36 are assigned orange class. So CART does this repeatedly, and you get a more and more, you get a finer and finer partition of your feature space, and that can be nicely represented in this tree structure. So every element here of this partition just corresponds to some terminal node on this tree. There's several details here which I'm going to leave out. One of critical choice of tuning parameter is how deep to grow this tree. So you could consider partitioning finer and finer. You could partition down to some level where you only have one object in each element of the partition. That's clearly too deep. So CART tries to balance how deeply to grow the tree through some cross-validation procedures. Once you have a classifier like CART, you want to test its performance. It's important to test its performance on data that wasn't used to construct the classifier. So typically you'll have test data which you hold out. You don't build the classifier and test data. Once you have your classifier, then you classify the test data with the classifier. And you can make something like a confusion matrix. So a confusion matrix is shown in this, the table on the slide. The rows here are the true class of the test data, and the columns are the predicted class of the test data. And you can see that what you want is the counts on the diagonal to be large. So that's saying that you classified these objects correctly. The actual class was black, and you classified the object as black. And then counts on the off diagonals are errors you made. So for 7 objects in the test data that were of the black class, but they were classified as orange, so misclassifications. I'm going to show how this works on a small variable star data set from OGLE. I mentioned OGLE yesterday. OGLE stands for the Optical Gravitational Lensing Experiment. OGLE has collected 400,000 plus variable sources, both in I-band and V-band. The sources are very well sampled in I-band, hundreds of measurements, and a few dozen measurements in V-band. There's a 10-year plus baseline for most of these objects, and all of them are available online at the OGLE database website. So to illustrate how CART works as a classifier, I just took 5 classes, 2 Myra classes, 1 Cepheid class, and 2 Lyrae classes. I then did feature extraction, so computed 4 features for every light curve. The features I computed are period, amplitude, skew of the magnitude measurements, and point-to-point scatter. Once we do feature extraction, we go from light curves, which are sort of a complicated object to deal with, to a feature matrix, which is a very nice object. In this slide, I've printed out the first 6 rows of the feature matrix. So the rows here are variable stars, and then the columns are features for that particular star. So there would be, I'm just looking at 500 sources from OGLE, so there'd be 500 rows in this matrix. The first 4 columns are for the features, and then there's this additional class column. And then I'm going to take 400 of these rows, use them as training data, and then have 100 rows as test data. Here I plotted a scatter plot matrix of the 4 features, and you can see here kind of what you'd expect, that the 2 Myra classes represented by the blue triangles and the black plus signs, those tend to be grouped together in feature space. And the Lyrae AB and Lyrae C are pretty close, but they tend to be far apart from the very different class of Myras. And the Cepheids are sort of somewhere in between on their own. So then you can grow or fit a CART model to that data. The result is this tree I plotted here. What's nice is now that even in dimension greater than 2, you can have a clear representation of what your classifier is doing with CART. So the way CART is going to classify a variable star is first it's going to look at a period, and if a period is less than 0.42, it's going to classify that star as being in Lyrae type C. If greater than 0.42, then it's going to move to the next decision point. And this is also a cut on period, so shorter periods than 0.89 days are classified as Lyrae AB. So something's going to be classified as an Lyrae AB only if its period is greater than 0.42 days and less than 0.89 days. And then for the next split is done on amplitude. So small amplitudes less than 0.75 are classified as Cepheids. And then you have what are essentially longer period and larger amplitude sources are then subsequently split by the point-to-point scatter feature and the period feature. So one thing that's nice about this CART tree is if you're an astronomer, you can recognize that these splits make astrophysical sense. So Lyraes have short periods, and Cepheids have smaller amplitudes than Miras. We can take the 100 sources that I left out of the training data that were assigned to the test data, predict their class, and then make a confusion matrix. And one thing that's nice here about the confusion matrix is it tells you a lot about where your classifier is making mistakes. So along the diagonal, that's where the classifier is making correct decisions. The off-diagonal elements for Myra O-rich and Myra C-rich are fairly large. So frequently, O-rich Myras are getting confused as C-rich Myras, and C-rich Myras are getting confused as being O-rich Myras. So that is very useful if you're looking to improve on a classifier. What this confusion matrix is telling you is that you need to develop better features for separating O and C-rich Myras, and then possibly refit the model to a richer feature set. CART, a question? Yeah. So this is an actual RRAB that's classified as a Cepheid. So I think what happened was, if you go back here, it could be that it had a particularly long period for an RR Lyrae. So it was, you had a test RR Lyrae that had maybe the longest period of all RR Lyraes in the set. And so then this, the split was made at a period that was possibly a bit too small. There's a couple things. One is the period estimate could be incorrect. The other thing is that like I said before, that RR Lyrae AB happened to have a long period. So RR Lyrae ABs can have periods up to about a day. So this is this cut is somewhat small at 0.9 days. That would be another possibility. Okay, so the confusion matrix tells us a bit about what features we might want to develop if we want to construct a better classifier. CART is quite interpretable. I showed the output of CART on the last slide. You can understand what it's doing. So CART is not a black box, but it's not a particularly accurate classifier. So there's it tends to be a bit of a trade-off between interpretability and accuracy for classifiers. Interpretable classifiers are usually a little bit less accurate. Random forest is now quite popular. Random forest is quite accurate, but it's not so interpretable. It's harder to understand how random forest is making decisions. CART also forms the basis for random forest. So CART, the T in CART is for trees. Random forest is growing or constructing many CART trees on bootstrapped sampled versions of your data set. So understanding random forest, a component to that involves understanding what CART is doing. So even though CART isn't frequently used in variable source classifiers today, in some ways it's still kind of at the basis of how random forest is working. Okay, so that's a little bit of background on how we can fit classifiers to variable stars, and now I'm going to talk about two challenges. So one is controlling computational costs in the feature extraction process. So there's many features that different groups are using to classify sources, and associated with each of these features is some sort of computational cost. So one feature is colors. So colors is the difference in mean magnitude between two bands. And in order to compute the say UG color, you just have to compute the mean magnitude in U band, or weighted mean in magnitude in U band, and the mean magnitude in G band, and take a difference. And that takes essentially no computational time. Ashish mentioned yesterday that there are these Stetson measures. These are for assessing whether an object is variable or not, and these are also very, very computationally quick to compute. But then we can move into features which are more computationally intense, but still not extremely computationally intense. So these would be things like period estimators, which will often take several seconds or a minute for a source. Or maybe more period estimation methods targeted towards a particular class. So Lyrae variables are one class of variable stars. They are quasi-periodic functions, so it's not necessarily a good idea to just fit a sine function, since not only are they not sinusoidal, but they're not actually even strictly periodic functions. So groups have developed methods for estimating periods for Lyraes and for characterizing their variability, and fitting those models and getting features from those models may take 20 seconds or so. But then you get into even more computationally intense features, which they take a long time to compute, but are potentially very, very useful in classification. So one example are Lyrae templates, which output some goodness of fit measures. So Branimir Cesar has done a lot of work on developing those from SDSS Stripe 82, and those can take 30 minutes or more to fit to a single object. And then David Jones yesterday spoke about generative models, which will output posterior probabilities. Those, we can think of those posterior probabilities themselves as being extremely useful features for doing classification. And potentially those are quite computationally intensive to compute. So there's a limit to how many of these features we can extract for each source. We certainly don't want to extract every feature for every source. So this is well known, and there's already some efforts being made to address this issue. So one common solution is to compute a cheap set of features for all sources. So if you have a survey where you're collecting 100 million sources, get these cheap features which take almost no computation time, so things like colors or Stetson J, build a classifier with those simple features, identify interesting objects, which are going to be a small subset of all objects that you have, and then you do follow-up classification on just the objects that you think are interesting. So to make this concrete, this is essentially what pretty much everyone does before they actually do variable star classification. They first do variable versus non-variable classification. And since there are so many objects there, when you're considering all variables and non-variables, typically you would compute simple metrics to separate variables from non-variables. So things like Stetson J, where you can compute it for every source in your survey. And then you can make cuts on those variability metrics like Stetson J, and then your variable sources are your interesting sources. You can compute more computationally intensive features on those sources and build a classifier just on the objects that you have classified as being variable. A few works have taken this a step further in a somewhat iterative manner. So one example is Cesar 2016. Cesar was trying to find R Lyrae among 500 million pan-stars light curves. So like many works, Cesar first identified variables among these 500 million light curves. So this reduces the number of sources down from 500 million to maybe 50 million. But even that is a large number of sources to compute some of these very computationally intensive features on. So as a intermediate step, some fairly simple features were computed on objects that had been classified as variables from classifier 1. So these simple features are things like multiband period estimates, amplitudes, and other features which you might be able to compute, which would take less than a minute per source. Once Cesar had computed these features, then a classifier was constructed on the variables, and certain objects were classified as being certainly not R Lyraes, and others were classified as being potential R Lyraes. So this is with a probabilistic classifier. Once the classifier outputs the sources which are likely to be R Lyrae in classifier 2, then you have a much smaller set of objects, and then you can compute some of these very computationally intensive features just on those objects. So those would be things like these template goodness of fit measures from these template fits. And at this point, you're really only computing those computationally intensive features on maybe 100,000 or so objects that are a few 100,000 of these 500 million, which you've identified as being likely RLIRA candidates. So I think this is an interesting idea, and I'd just like to kind of formalize this a little bit, because I don't think it's been studied so much in statistics, or at least I haven't seen it. So in the standard setting, we have a light curve L, and we have a function f, which maps light curves to features. So x here is going to be some vector of features for light curve L, so that could include things like periods and colors and so on. And associated with light curve L is some class z. And then c hat is our classifier, and when we're training our classifier, our goal is to maximize the probability of making a correct classification. So CART or random forest or whatever, it's finding the classifier c hat that maximizes accuracy. But this ignores any notion that this feature extraction step could have taken a long time. So one way to look at this would be to say, well, we're going to have a classifier which is going to choose which features it's going to extract for each object. So c hat no longer is a map from feature space to classes. It's a map from light curves to a class prediction and a time t that c hat used to compute features for light curve L. So z hat is the predicted class made by the classifier c hat, and t is the amount of computation time that c hat used to make this prediction. So that was the amount of time that was used to compute these features. And then we can say, well, can we train a classifier c hat to maximize the probability of making a correct classification, but subject to some constraint on computation time? Like we want the expected computation time to be less than some number we choose, t0. And the result of this would be that if we have capital N objects, this might be hundreds of millions or billions of objects, that the total computation time to classify all of them, it will be around capital N times t0. And I'm not sure if this has been looked at much in the statistics literature, or if there are ways of actually constructing classifiers in order to minimize feature computations. If you know about such methods, please speak to me about them. Okay, I have 2 minutes left, so I'll go quickly through post-classification inference. I mentioned this a little bit yesterday. One of the big questions in astronomy is how far away objects are. If we want to have much understanding of the universe, we need to know where objects are. It's difficult to determine how far away objects are because the distance to an object is degenerate with its luminosity, and in general, we only measure a star's or an object's brightness. We don't know its luminosity, which means we don't know its distance. So one way to address this, astronomers have many ways to address this, but one method for addressing this is through standard candles. So standard candles are classes of objects, all of which have the same luminosity, or approximately the same luminosity. So if we can determine that an object belongs to a standard candle class, then we know its luminosity, we know its brightness, that's how much light we observe in the telescope, and then we can determine its distance. And one reason why some of these variable stars are interesting is because they're standard candles. So auroral Lyraes are an example of a standard candle. They all have approximately the same luminosity. Here's an example of an auroral Lyrae. On the left is an unfolded auroral Lyrae light curve, and on the right is the folded light curve after you've estimated the period and plotted, instead of time, plotted time modulo period. So these aren't exactly standard candles. You have to account for things like dust and the PL relation. But once you have an object that you know is an auroral Lyrae, you can estimate a distance to it. So I'm going to talk about very briefly talk about one effort to use auroral arrays as standard candles to map the Milky Way halo. So the Sloan Digital Sky Survey, we've heard a little bit about it in the past 2 days. It discovered 60,000 variable stars along an equatorial stripe, all at declination approximately 0. So this salmon colored region is SDSS stripe 82. So there were 60,000 variable sources found in this region, and there are about 250 brightness measurements for each source. And these variables belong to many different classes. So I showed you an auroral array from these 60,000, but there's also eclipsing binaries, lots of quasars, all sorts of objects. And one thing that you can do with these, or that Cesar 2010 did, was to extract features for all 60,000 variables and try to find the auroral array. So Cesar was able to find 350 auroral array subtype AB in SDSS stripe 82. Step 2 was not done using a formal statistical classifier. What Cesar did was compute things like color and periods, and then find regions in feature space where he thought all objects were auroral arrays. So once you find the auroral arrays, you can estimate distances to the auroral arrays. So an illustration of that here is in step 3. Each point here is an auroral array. Along the angular axis is the right ascension. All of these objects are at declination approximately 0, so you're looking out into stripe 82. And then kiloparsecs is on the x-axis here, so this is distance from, this is heliocentric distance, so distance from the sun to any one of these 350 auroral array. And to give a perspective about how far away we're looking, the Milky Way and its spiral arms are plotted in the center of this plot, and then we're looking out into what's known as the Milky Way halo, and then we are characterizing where, or Cesar is characterizing where structure is in this halo. So there's a lot of auroral arrays in this region that corresponds to this region up here. And so what Cesar is doing is using auroral arrays to determine the structure of the Milky Way halo, which is of interest for several reasons. Cosmological simulations predict certain structures in the Milky Way halo, and then we can compare what cosmological simulations to predict to what we observe. There's various groups that are working on extending Cesar's work to larger regions of the sky. Cesar was just looking at SDSS stripe 82, but for example, the Dark Energy Survey is covering this blue region, much larger than SDSS stripe 82. DES is also going deeper. So potentially we can make these maps of the Milky Way halos over a much larger region of sky. A challenge with DES is that the light curves are extremely sparsely sampled, so there's only 50 total observations across 5 filters. Cesar is also extending the results from SDSS stripe 82 to the whole Pan-STARRS sample. So the reason I bring this up is that these classifiers, which played a role in, which Cesar is currently using now for Pan-STARRS, in which me and some collaborators are working with on the DES data. These play a role, we don't just classify the auroral array, we then estimate distances to the auroral array, and then we estimate intensity maps to find the distribution of matter in the Milky Way halo. So there's several inference steps post-classification, and sort of one concern or question I have is how can we propagate uncertainty from that's being introduced by the classifier all the way to the stage where we are making these intensity maps, because clearly mistakes that are made in step 1 here are affecting the intensity maps that we make in step 3. So that's all I have. Thank you.